Now that we've warmed up a bit by implementing maps and folds, we'll dive right into it. In this video, we'll be working on a poker hand ranking function. We will see whether FPGAs are worth putting our faith in. Right now, we are very scared. We know that in theory, FPGAs could give us huge benefits when doing reinforcement learning, but can we actually get those in practice? It is just so hard to believe, but leaving it at that would be too unfair to FPGAs, so we will give them a proper chance. The hand ranker that we'll show you is something we had already written in the past in Spiral, so we'll bring it into this new project. It has a ton of type errors due to the various missing conversion functions, so we'll bring those in while we are at it. This code was originally written for Cython, so we will have to port it piece by piece. And looking at the resulting hand ranker function, we realize that we have a big problem. All the functions are using tail recursive loops, but the Xilinx HLS manual mentioned that recursion isn't allowed in it. So right now we have a tough job in front of us. Do we rewrite all of this so it uses regular C-style loops? Honestly, we don't feel like it. Rather, we might as well inline all of these instead. This would be possible due to all the hand pattern checking functions having statically known loop sizes. Okay, we are going to have to slow down here a little. The video has been going at 4x, but going over the code, we think it is basically unreadable, and as much as we'd like to just jump in and start remodeling it, we are going to have to do a review of what it is actually doing. We'll have to build a model of it, so let us get started. The main problem, and why the code is so unreadable, is that most of the functionality is being done through bitwise operations, so the primitive integer types tell us very little of what is supposed to be going on. We'll have to draw pictures instead to figure it out. First, let's talk about the number of ways a poker card could be represented. One of the ways is to simply have it be a binary number between 0 and 52, representing the index of such a card in a deck of cards. 13 cards for every suit. We can lay them out neatly like this. And this is what the two functions we are considering, namely suit and rank, are receiving. They get a card represented as such and extract its rank and suit into an 8-bit int. The function named full does the inverse of that. Arguably, understanding these three is easy. Let's see whether we can figure out what the rest are doing just by looking at them. Let's ignore the top-level function for a bit to talk about the score hand function. As you can see, the score itself is just one of the 9 different types a hand can take, going from high card to straight flush. The score itself is shifted to the left by 32 bits, and in the first 32 bits, a hand is supposed to be packed. But it is a mystery even to us, the ones who wrote this code, what the hand is supposed to be representing. It isn't a card, and it does not represent a bit field of all the cards in the deck. So what is it? If we look at the top-level function, we get a similarly perplexing situation. It takes in a bool and a variable called suit ranks. It is a type that is called hand, but underneath, how is that hand being represented? We'll add a bunch of question marks around these two variables. With the perplexing mysteries established, let's move on to the next part. And once we put the update and the has card functions into the canvas, it all comes together, at least for us, and we remember completely why this was designed the way it was. Let's talk about the has card function. What it is doing is checking if a particular card is present in the hand, the one that was given in the top-level function. That full V expression tells us what the EV input argument is, just a suit and a rank in a spiral record. It can only be a number from 0 to 52. Once we have that card index, we bit shift the original hand given in the top-level function to the right by it, and mask out all but the first bit. If that bit is 1, then the card is present in the hand, otherwise it is not. Therefore, here is how the suit ranks variable is laid out. It is a bit field of 52 bits, and we are using a 64-bit int to represent it, with the final 12 bits being unused. Just imagine the stacked deck at the beginning being laid out in memory from start to finish. It can have an arbitrary number of bits set to 1. For example, if we were playing Texas Hold'em, we would have 7 bits set to 1 when the suit ranks argument is passed into the score function. If we were playing Omaha, we'd have 9 cards in the hand, and conversely, 9 bits would be set. That takes care of the mystery of the hand argument passed into the score function. The reason it is named suit hands is because if it were a 2D array, the suit dimension would be the outermost one. Let's go over the update function next. Studying it reveals what the isFull variable is doing. That should have been a bitwise OR instead of an integer addition, and it would have made the code clearer had it been the former. It would have communicated the intent of this function better and have been more efficient to boot. We'll fix that in the FPGA implementation. What this function is doing is adding the cards to the hand. Imagine if the hand argument were an array. What this function does is the equivalent of pushing those suit and rank variables, the ones in the spiral record, into it. The bit array, as it were, can hold a maximum of 5 hands, and we can do at most 5 bitwise shifts to the left before the data inside it gets truncated. And that is enough, because at Showdown, only 5 cards can make up a poker hand. They are collected here from highest to lowest. Suppose we put the score as the most significant bits, and in the hand we leave out the suits and keep only the ranks. Then it becomes very easy to compare the cards using an integer comparison. The scores would always determine the winning hand as they'd contribute the most to the value of the hand. But if they are tied, then it would come to just the matching between the rank values. As for why you'd want to keep the suits in, that would be to extract them from the hand for later printing. We are not saying this is the best way to do it, but it was convenient at the time, and on an FPGA, we'll have a lot of opportunity to optimize all of this. The suits and the ranks seem complicated at first because of all the bitwise operations, but what they are doing is getting the count of suits at a particular rank index, and ranks at a particular suit index respectively. For a given rank index, the number of ranks can only be 4 different suited cards as well as none, a total of 5 different values. But for a given suit index, there can be 13 possible rank cards, as well as none, for a total of 14 different values. As we are testing the number of ranks or suits frequently in the looping functions we'll come to later, we thought it would be best to pre-calculate these values so that we might take advantage of that down the road. The straight rank function adjusts the rank of aces when trying to index below 0. Reading this function is making us realize that the way we've arranged the aces is misleading, and they really should come after the kings, at the very end instead of being the first. Just keep that in mind going forward. This function is a utility, so we don't have to make a special case when pattern matching on straights. Aces can act as the beginning of a sequence, such as ace, 2, 3, and also come at the end of straights, such as queen, king, ace. Thanks to this function, we can keep our loops neat and tidy. Let's move on. You'll understand what it does once you see the function for detecting straight hands. The update ranks function iterates over suits of a specific rank and pushes those suits into the bit field array. You might be wondering whether taking in this count is necessary, and that is something we are wondering as well. We'll keep that in mind for later. It might be better to redesign the whole score function so they aren't necessary. Since this function has been tested, it should be able to serve as a baseline in the test bench. The update all function is what the hand score detectors call to get the kicker cards after the main pattern matching has been done. For straights and flushes, that isn't necessary, but the pair-type hands, the single pair, 2-pair, triples, full houses, and quad hands need the kickers in order to compare the final score. So, what this does is loop over all the possible hands from highest to lowest and adds the cards from the total hand to the showdown one. It takes in the count argument, C, for how many hands should be added to the hand. Arguably, this function could be simplified. Instead of taking in a compile time list of exclusions, it might be better to zero out the cards in the original hand instead. We are going to try out that kind of design going forward. As you look at the design of this function, some amongst you might be wondering, instead of looping all the possible cards in the deck and testing the bit field along the way, would it not be better instead to store them in an array? One argument that comes to us is that using heap-allocated arrays is very slow, but the primitive integers we are using here can be kept in registers, so the CPU would churn through them very quickly. And this is true in Cython, for which this code was originally written for. Cython advertises itself as fast alternative to Python, but as soon as you introduce any allocation of Python objects or start doing function calls and passing them into functions, the overhead of reference counting and heap allocation will absolutely kill your performance. We once benchmarked a pickler combinator made in spiral targeting Cython and the F# backends, and the F-sharp backend was 1,000 times faster. That was because one of the loops was allocating an array at the start of the program, and this was just so much faster on the .NET platform. Anyway, the design we are going to adopt for an FPGA is not this. Instead, we will take advantage of the fact that FPGAs have not just 8 on 16 to 32 and 64-bit integers as primitives like CPUs do, but can have integers of arbitrary bit size instead. We'll do things the right way the first time around. We won't go into depth anymore on what the individual hand detectors are doing. Let's instead try compiling this and seeing at what point the HLS C++ compiler by Xilinx starts complaining about recursion. After that, in the next video, we'll do a proper tutorial for Spiral that goes over its main features from start to finish. We want to go into a time-lapse, so we can focus on rewriting all of this. And these videos are very distracting for us. We want to just put on some music and focus on programming for the hard stuff. Anyway, what you are seeing in the background is Ghostlike trying to get the C synthesis to run. We have to first set the top-level function in the project settings. We run into a few bugs in the HLS C++ backend for Spiral while making this video. New version will be out shortly. We'll change the backend so it prints the C strings as const char pointers instead of regular ones. As you are watching this, let us say that beyond small fragments, you are not expected to understand the compiled output. In fact, it is a waste of time to try to understand it. You just have to have faith that if your high-level reasoning is correct, then unless given reason to suspect otherwise, the low-level compilation output will also be correct. This is something we always do when it comes to programming languages. It is very rare that we look at the generated assembly. As you can see in the terminal, when we try to do C synthesis, we get errors that recursive function calls are not allowed. This is really a pity, but we couldn't have possibly anticipated this situation when we were writing that code originally. We were always thinking that various kinds of AI chips would have come out that would make the design worth it. And we didn't know much of anything about FPGAs. We can't blame ourselves too much for getting it wrong in this case. The design that will be specific for them will be much better. We'll do it even without tail recursion. If you liked this video, like and subscribe, and in the next one, we will slow down a bit to do a tutorial on Spiral basics. We'll go over language features in the manual, and you'll see that Spiral is quite simple. Even more so as far as the HLS backend is concerned. It is hard to master, but in our personal opinion, if you are working on esoteric, hard-to-program hardware, then it is very much worth it. FPGAs have exactly the profile of what we designed Spiral for. If it cannot do it, no language will be able to do it, and we have wasted over half a decade of our life making Spiral. We won't let it come to that. We will continue to fight.